Hello, you are welcome to this new series of bending stresses in a beam. Bending stresses in a beam. Now, this chapter here is not really different from our sharing force and our beam and our bending moment calculation. It's just like an advancement into like applications of it and further advancement. So now, bending stresses. Now, the first thing that you need to know in bending stresses to solve a lot of equations is the bending equation, and the bending equation is given as m over I is equals to phi sigma over y, which is equals to Young modulus E over radius R. Now, this is the bending moment, the bending equation. Given that M is the bending moment, that is the bending moment of the beam, while I is the moment of inertia, the sigma phi is the shearing stress, the tensile stress, and y is the centroidal distance from the center of the centroidal distance of the beam. We have E is equals to Young modulus and R is equals to the radius of curvature, the radius of the bending of the beam. That is the radius of how the beam bends. Let's say we have a straight beam, the radius is 0. When load is applied on it, it bends somehow like this, then it creates a radius here. So we have a radius R here, we have theta here. So now this radius here is the radius that is under the Young modulus right here. So now let us go deeper into this. Now, talking about the bending equation, there are some things here that you might not actually be familiar with, which is number one, which is the moment of inertia. Now, the moment of inertia is a very very fundamental part in solving bending stresses equation, and it is given by let's say I of x is equals to integral of y square dt. That is the formula for in that's the formula for moment of inertia. You and I might have actually crammed a couple of formulas on moment of inertia, like the rectangle formula, which is bd cube over 12, or the circle formula, which is pi d raised to power 4 over 64, or other formulas like that, like the formula of the triangle, which is um bd cube over 36, and so on and so forth. But I want to break this moment of inertia down into bit by bit. So before we go into moment of inertia, we first have to understand what is called the centroidal distance. That is the centroid distance y. Let's say we have a rectangle here. The centroidal distance is the line that passes through, like the line at which the thing balances, and the centroidal distance at axis xx here, which is, let's say this is distance d, and this is base b. We have this is base b and depth d. The centroidal distance between of this along axis xx is y is equals to d over 2, and y equals to d over 2 is for a rectangle. The formula for centroidal distance of a rectangle does not apply to that of a triangle, does not apply to that of other like trapezium and so on and so forth. For example, let's take a triangle for example. Now in triangle, the centroidal distance here is located y is equals to d over 3. That is, the total depth here is d, where we have base b here. The centroidal distance y is equals to d over 3. So that is the centroidal distance of a triangle. And for a circle, the centroidal distance is d over 2, which is the radius. So that is for that of centroidal distance. Now that we know about centroidal distance, we can go forward into the moment of inertia. We can move forward into the moment of inertia. Now let's take a box. Let's take a rectangle right here, and now I cut the rectangle into a tiny slit. Let's say this is the entire distance d. I cut the rectangle into a tiny slit, like a part of the rectangle which is given by the y. The rectangle is given by the y. Let's say the base distance is b, the distance of the base and the depth. So now given by the y, now I want to find for the moment of inertia along the x-axis. Now you are hearing that I'm mentioning along the x-axis, along the x-axis. The reason why I'm using along the x-axis is because solving moment of inertia along the x-axis, this is the formula for it. If we are solving the moment of inertia along the y-axis, the formula would be x square dA. And what it means is that we are finding for the moment of inertia of this box along this strip right here instead of this strip right here. Like we are not finding for the moment of inertia of that strip, but like calculating the strip from parts. And the centroid that we are going to be using is the centroid of this distance um, y y axis, the centroid of the y axis. But here we are using the centroid of the x axis. That is why we are using the moment of inertia of the x axis. So that is that. So now moving on, we have the moment of inertia equals to y square dA. Now this dA is the infinitesimal area, like the small change in area, and this dA is given as b dy, that is this base here times this small change dy right here. That one will give you the area of this tiny strip right here. So that is our formula, our dA right here. So from here we can know that, and then we know that if we have this thing that goes through the middle, the distance from here to here will be d over 2, and distance from here to here will be d over 2. But if this is the x-axis, whereby that is the neutral, here will be the negative and here will be the positive. So therefore the values up, and the upper limit and the lower limit would be d over 2 and minus d over 2. So we have our moment of inertia along the x-axis to be equals to full integral d over 2 minus d over 2 of b, this b I brought it to the back of y square, then I put my dy. So now as I continue integrating, I have my I of x at b open bracket, we have y cube over 3, then we impute our d over 2 minus d over minus d over 2. So right here we can bring 1 over 3 outside, because 1 over 3 has nothing to do with it. So we have I of x is equals to b over 3. We brought our 1 over 3 outside, and now imputing those d over 2 and minus d over 2, we have d cube over 2 cube, which is 8, minus, then this minus d, we have minus d cube all over 2 cube, which is 8. So if we continue, we have our ix is equals to b over 3 open bracket, d cube, this thing will become plus, and then when it becomes plus, it's going to add, it's going to add it's going to add together, and we are going to have d, we are going to have something like 2d cube over 8, whereby 2 will cancel and it will remain 4. So at the end of the day, we are going to be having d cube over 4. So when we multiply this together, it's going to give us bd cube over 3 times 4, 12. Now that is where we got the formula for the moment of inertia of a rectangle. We can also find for the moment of inertia of a circle while we are at this. Now, finding for the moment of inertia of a circle, you need to have a little bit deeper knowledge of calculus, whereby you change units from polar coordinates to Cartesian coordinates and stuff like that. So that is what it's about. So now let's imagine a circle right here. This is not a perfect circle, but I just a circle that is like this, whereby this is center divided by 2 here, and let's say that we have a little strip here. This is the strip here, we have here and here. Now this is the region of the A inside the formula, whereby we use the integral of y square dA. Now this region here is the A, and in this region the A, we have this small arc here to be the theta, and here to be the r. We also have our r to be the length from here to here. So we have the theta and we have our the r right here. So finding for the value of this. Now dA, we have our dA is equals to r d theta dr. If you are good at converting coordinates, that is what it's going to give you. It's going to be r d theta dr. So then that is for that. Then for the y side is this small change in arc, the theta. So now what is the theta? The theta now is equals to, let's take this place to be theta. We have sine theta, which is the main theta that we have here. The main theta we have here. Sine theta is equals to, we have our opposite, which is the theta, divided by our length r, that is the full length from here to here, that is the length there, our the theta over r. So that means if we cross multiply, we have our d theta is equals to r sine theta. So that is our d theta. So and y is equals to our theta. So therefore this would be equals to, since this will be square, we have r square sine square theta, then we have our r d theta dr. R d theta dr. How can multiply this? Um, we have how can multiply this? We have r cube sine square theta d theta to the r, and the units here are pi, I think pi over 2, then minus pi over 2. Those are the unit size here. So now since this is this, now in calculus, if we have something like this where the r is not directly, it does not affect the value of theta, and theta does not affect the value of r, they are like independent variables, they can become something like this. We have integral of pi over 2 minus pi over 2 r cube dr times the integral of pi over 2 minus pi over 2 times sine square theta d theta, and sine square theta d theta. So if you continue this, we continue this, and we continue, we are going to have we have r raised to power 4 whole over 4, everything from pi. No, this is not pi, this, the value of r is supposed to be from r here. This will also be a double integral, where we have r to 0 is supposed to be a double integral, since this is polar coordinate. So we have from r to 0, this is also be from r to 0. So this one will be r to 0, and the other side will be in sine square theta. We are going to have 2 sine theta cos theta, 2 sin theta cos theta. Then we have from pi over 2 to minus pi over 2, from pi over 2 to minus pi over 2. So after solving this and you continually solving this, I might not be able to go on much longer. At the end of the day, when you solve this, you are going to get our I of x to be equals to pi r raised to power 4 all over something, I think 8, which is the same thing as pi r raised to power 4 by d raised power 4 all over 64, by d raised power 4 all over 64, by r raised power 4 all over um, um, yeah, okay, by r raised power 4 all over 4, which is the same thing as by d raised power 4 all over 64. That is what you are going to get after you continue solving. But the entire process is the process of double integral in solving this.